Encrypted disks must be managed in some way, especially in companies. We need to have the possibility of remote administration and remote program configuration that will encrypt and decrypt data. After all, we will not do it to each computer separately. In addition, some embedded emergency mode is mandatory. What do you do in a situation when a user we encrypted data for, or the user encrypted the entire disk himself, forgets a password? For example, the password that allows him to decrypt the disk. There must be some way to decrypt data on the disk on behalf of the user. Of course, this affects security because it's based on trust to the administrator. Additional benefits of programs that encrypt the disks could be something like hiding the fact of the presence of data on the disk. This is something that has not been implemented in BitLocker. This is something that makes TrueCrypt stand out as compared to BitLocker. TrueCrypt has such functionality that when one disk is encrypted, it will create a second disk encrypted with a different key. Since both these disks are encrypted, the analysis of these disks' content, for example when the computer is off, does not show any difference between one encrypted disk and the other. In general, it should be maximum pseudo-random data. Now, if someone asks us to decrypt a disk, in most cases those who are authorized to do so, such as the police, if they ask us, we have the obligation to reveal to them the password for this type of security. If we have the password to one disk, it will be decrypted and its content made available. If, however, we don't give a second password, everything that was encrypted and was on the internal hard disk will remain invisible, at least in theory. An additional advantage to disk encryption could also be checking the integrity of the computer. This function is only available in BitLocker and is not available in TrueCrypt. Its idea is that interference in the computer, for example moving the hard disk or a change in the order of the starting devices, causes automatic blocking of the encrypted disk. We've already mentioned authenticity. We said that a signature is used for it. However, in the case of disks, that's not possible since the sector has a fixed sector size. We can't force manufacturers of hard disks and low-level software to reserve for us a few extra bytes in each sector. We also can't write checksums to another sector, since there are programs that are based on the fact that sectors are independent of each other. Examples of such programs are database servers, which in their own way manage writing and reading. It cannot be that a change in data in one sector causes their automatic change in another sector. This is what would happen if a checksum were there. We could solve the problem by artificially doubling the size of the sector. Then all the problems are solved. We have a lot of space for the checksum. In addition, the operating system sees only half of the sectors and there are no relationship between the sectors. Unfortunately, we'd have to convince users that when buying, for example, a 500 gigabyte disk, it really has to be 250 gigabytes. We could meet some resistance. Therefore, disk encryption software, instead of using MAC signatures, broadcasts bits on as many sectors as possible. In addition to encryption, specific sectors use keys to avoid simple mathematic relationship. Well then, how can we encrypt our hard disk? The first decision we make is the choice of algorithm. Most often we can choose Advanced Encryption Standard, AES. This algorithm won the competition for successor of the DES algorithm, which was started in 1997 and lasted for the following 3 years. It was a moment in time when it was repeatedly proven that DES can be cracked in less than 24 hours. It was time for it to be changed. The change occurred through an open competition. Anyone could submit an algorithm proposal. For 3 years, professionals, mathematicians and cryptographers, analyzed the actions of various algorithms and tried to crack them. AES won the competition. Thus, its security was confirmed. In addition, AES is relatively quick, insofar as that we can use 128-bit keys. The disadvantage of AES is that if we double the key length, the encryption and decryption process is clearly slowed down. Performance may be 40 or 50% lower. Without a doubt, its advantage is its resistance to certain sophisticated cryptanalysis attempts. Together with this, more and more popular are single-chip processors. They're both more powerful and more functional, performing more and more tasks. We can use single-chip processors to encrypt. It turned out, however, that safe algorithms implemented in single-chip processors are not that safe. You can get the key from them by analyzing the data transferred between individual blocks, between physical devices soldered on the keyboard. Among other things, you can see the power consumption of individual microcircuits. This is important because certain operations require more power than others. For example, multiplication is more expensive than addition. There's also a relationship between the key and the cost of operation, which can be precisely measured using, for example, an oscilloscope. Multiplication by 0, for example, is always faster and requires less resources than multiplication by any other number. Analyzing the data transferred between the modules, conclusions can be made regarding the construction of the key. An interesting fact is that in order to protect against such attacks, the creators of these single-chip solutions started to protect critically important modules with paste. After removing the housing, immediately saw where the interesting modules are. AES is designed to balance the number of different operations, such as addition and multiplication. It's resistant to this type of analysis. When selecting an encryption algorithm, we also have the choice of the serpent algorithm. This is just as safe as the AES algorithm, but clearly much slower and non-standard. This algorithm took second place in the competition. The next algorithm is two-fish. This is Bruce Schneier's algorithm, who also participated in the competition.